Okay, folks, I'm sure you all have questions, and I'm gonna get to those, but I'm gonna start off with a couple of problems. Some of them on the quiz. Okay, the first one, I'm actually kind of use common sense a little bit, and then we'll verify. That is, but. Say this is y equals 4 minus x squared. Find interval 2 that maximizes area. So I can move. So let's say that's too long. I can move this interval anywhere here and compute the area of the curve. Right now, it's over here. That's clearly not maximum because the area is actually negative. Right? Because so would everybody agree that the interval 1, 2 be somewhere here? And by the way, it's 0 minus 2, 0. Anybody want to guess for the interval 1, 2? That's actually negative. Who would guess? That's a great guess. That's right. It seems to be like if I take this interval 1, 2, that's going to make the area under the curve biggest. Right? It seems if I move it a little bit this way, I'll lose a little area, right? Because I've got sort of the apex of the curve. Right? Let's see this in action. Let's sort of do this out. And I'm going to do this and I'm going to do it on a quiz yesterday. And I'm going to brain teaser. So we're going to maximize, let's say, area of the curve. Where do I start? I don't know. I'll start at A. Then I'll go to A plus 2. This signifies that my interval can start anywhere, but it's too long. Ready? This gives you, this is a formula that gives you the area under this curve, and it could be negative here. It gives you the same value, it's integral of A plus A. We want to maximize that interval depending on A. Right? Find the A that makes this as big as humanly possible. What do we do? What's the tool we use when we want to maximize something? Almost always taking a derivative. And here, by the way, I can start anywhere I'm set. So let's take a derivative. And this is the fundamental theorem of calculus. This is plug in top times the derivative of top, 1. Remember now, A is a variable. So let me vary. Minus plug in bottom times the derivative of bottom. Let's see what this derivative works out today. This is 4 minus A squared plus 4A plus 4 minus 4 plus A squared. So this is 4 minus A squared minus 4A minus 4 minus 4 plus A squared. So this looks like the A squared is canceled. And I get minus 4A minus 4. So the derivative of this minus 4a. What do I do with my derivative? Well, I got to gather critical numbers, that is places where this is either 0 or undefined. Minus 4a minus 4, never undefined. 7 equals 0. So I get a, and this is looking very much like your prediction, isn't it? Right? Minus 1 to 1. Right? Go there up to. We need to really verify that this does give a maximum. You can make a geometric argument here. Derivative. A prime a got one critical number and first minus 1. And we'll see when here's the derivative. When a is less than minus 1, like minus 2, this is going to be positive. And when a is bigger than negative, 0 is going to be negative. So you're increasing, decreasing, and this is a local max. In fact, it's an absolute max. And this sort of job. By the way, check this out. Notice that the height of the endpoints is the same. It bows up a little bit here, but the height of the two endpoints. Here's one that we did. Any questions? All right. One of the things we did yesterday, and I want to go over this. I want to go over the maximum column and the graph of this. The first thing I asked you to do concerning this function was to graph this. Okay, let's see what this is. I'm going to make a couple of observations. First of all, what's the domain of this? Everything's in 0. What do you suppose happens near 0? When x is very, very close to 0, but it's positive, that's almost 0. And that's humongous. When x gets very, very close to 0, but it's negative, still close to 0, humongous negative. What are you supposed to happen to 0? What is x to 0? It's verticalized. Now, notice as x goes to infinity, this goes to infinity, and as x goes to negative infinity, this goes to negative infinity as well, which can be more descriptive than that, because this one actually has a slant aspect. As x goes to plus or minus infinity, 4 over x goes to 0. Right? So this means h of x is very close to x. When x is big, positive, or large negative number, then this function gets close to x, because for large values of x, h of x is property for that. Right? So already I know this has got a vertical asymptote of 0, and I know for very large negative, very large positive values, this is very much like time flex. We'll see that reflected. The concavity tells us about that thing. Okay. Need a couple of derivatives here. And double prime x is a This gives you critical number plus or minus 2. And x equals 0 is not a critical number because it's not the domain of the function, but needs to be on part of our analysis. And for the second critical column, I worry about is 0. Okay, so let's do an analysis here. Okay, this is my first derivative. What happens to this thing when x is very, very large, say bigger than 2, like 100? This is 1 minus a small number. What happens when this thing is between 0 and 2, so something like 1 minus negative? What happens when this thing is very near, or I'm sorry, it's between -2 and 0, so like -1, it's negative. Yeah. And what happens when this number is very, very large, negative 100? And so the behavior of my function is decrease, decrease, decrease. And a local max, at -2, whatever I get, I'll put -2 here, -2, 4. And here, it'll open in 2. And here, vertical asymptote. Any questions on this? Let's look at the second derivative. This is let's see, when x is negative, it's negative. When x is positive, it's positive. So we have concave up, concave down, concave up. And what happens to 0? But it's not a trick. Why is it not? It's an asymptote, right? Certainly the concavity changes, but there is no point at 2. But so I think I just know in the office pretty well. And I'm going to use the structure. I know I've got a vertical asymptote right here, and I'm going to bubble on y for x. That's going to be that slant asymptote. Let's see what happens here. I got a local max -2 -4. Right there. I've got a local min at 2, 4. So let me look at it on the right side of the asymptote. What happens on the right side of the asymptote? It decreases off the asymptote, always smiling, gets closer to this. So and what happens over here? It's always frowning. It increases to the max and then decreases down to the asymptote. Yes. Questions? Okay. I asked another question about this function. And this is very similar to the one that I did first. The question was, find the interval of length 3, for which the area under the curve is minimal. Such that equals A equals 3, where A is bigger than 0. I did also say that. Where area under curve is minimal. Okay, so here's what I'm looking at. A plus 3 scale. Where the area under this curve is minimal. Notice as I slide A out this way, it gets bigger and bigger. Right, area under the curve. And actually, it looks like if I slide it this way, it gets pretty big, but boy, doesn't that get tall. If I agree with that. So would you all sort of guess somewhere in the middle here, there's a place where the area under the curve is as small as possible? Seems like there's an answer. Number one, first question, why did I say A is bigger than 0? Okay. The first problem is if you have an interval of 1, 3 over here, you go this way, the area is getting its negatives. So there's different, right? As you slide way out here, this is going down, 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 down. So the area under the curve will actually be negative, there will be no net, right? First problem. Second problem, if the interval actually gets this vertical asymptote, I don't know what the heck. Right? So I wanted to start to the right of 0. Okay, everybody understands the problem we're trying to solve. Okay, let's set her up. So, trying to maximize area of the curve, starting at A, going to A plus 3. Notice I didn't ask you. I didn't ask you what the minimal area is, although you can answer. Just ask what's the interval. Where do you start? Where do you finish? And because the interval is blink 3, if I start at A, I have to end at A plus. Right? Okay. And here, what's my playground? It has to be nice. Why? Because that's what I told you. Take a derivative. Fundamental theorem of calculus helping me out. This is plug in A plus 3. And multiply by the derivative of A plus 3. Remember, A is my variable. Derivative of A is 1. Minus, plug in bottom. And through A. Straighten this all out. A plus 3, 4 over A plus 3, minus A minus 4 over A. And let's see here. I've got 3 still hanging around. The 2 A's cancel further out. And I get this strength that's here. It might be convenient for me to put this single fraction. Four A minus 4A minus 4. So finally, looks like the answer is 3 minus 12 over A plus A plus 3. Now, two things that jump out at me when I'm looking for critical numbers are A equals 0 and negative 3, because these two make this denominator 0. Agreed? Somebody tell me, why do I not have to worry about either one of those bicycles? Right, these are not in my playground, they're not in my sandbox. I don't have to worry about it. So I'm only left with trying to figure out where this is equal. So set this equal to 0. And I get 3, 12, A plus 3. So 3, A plus 3, 4, A plus 3, 12, is equal to 4. And so I get A squared plus 3A minus 4 in this factor. So I get A equals minus 4, 1. And once again, I've got a third one. It's not my playground. Negative 4. No concern to me. So I get a critical number. A1 only critical. So, I guess I can erase this now, since it's only important about it. What I need to do, of course, is verify that this actually gives me a minimum. This could be a maximum, or it could be a red herring. Doesn't seem this way. Again, you can argue geometrically that this has to be minimum. No way it's maximum. But we'll check it this way. Prime A. Now remember, my playground starts at 0 and goes on forever. I don't have to worry about negatives. I have one and only one critical number. I have 1. And my derivative was somewhere here. A prime of A is 3 minus 12 over A equals. Now, I really don't have to plug it in. I could. But what I'm going to do is I'm going to do this. What happens to A prime, this thing right here, when A is very, very close to 0? And remember, it has to be positive. It's a little bit bigger. 3 minus, notice what we have here is a denominator that's very close to 0. So it's minus 12 divided by a very, very tiny number. So this is a huge negative. So this is negative. Then if 1 is 0, now what happens to the derivative when A is humongous? 3 minus 12 divided by a zillion, still about 3. Positive. So this is a local max and is absolute max. When you only consider 0 to infinity. Thank you. And it's an absolute min when you only consider 0 to infinity. Right? Over here it gets smaller, but that's outside. So the actual interval is 1. This gives. If I asked you to find the minimum area of the curve, this is the interval from 1 to 4 of x plus 4 over x. And it says 1/2 x squared is 4 log x. When I plug in 4, that's 8. That's 4 log 4. Minus, when I plug in 1, it's 1/2. And logging 0. So I get something like 15 halves plus 4 log. That's the minimum area. There's one more thing that I want to, and by the way, my picture on here. I'm going to point one more thing out. The original function, we're finding the area of the curve. The interval was 1 to 4. We gave them there. What happens when you plug in 1 to this? You get it's 5. So that means if I drew this correctly, so this what I've got drawn on here actually is not the minimum. When the minimum is achieved, at the 2 endpoints, you have the same. So maybe the minimum variance. This. Notice this is the same thing that happened at the other problem. Remember how I pointed out that at the endpoints the y coordinate was the same? It's like it is here. It's coincidence. So that's your extra credit. Suppose you have the area under a curve, you get either a min or a max on a finite interval like this. Show that at the 2 endpoints, the y coordinate is the same. Or give me an example where it's different. So that's just fun. Okay. Any questions? Okay, so let's get back to your questions. Yes. All right, so we're going to look at number 6. And examine what you mean. Our example. Same one, number 6 says Consider the curve defined by the equation x plus y squared equals x minus y cubed. Okay, so this is one of these kind of implicit things. Okay, well, I'm gonna, okay, right. Number A. This was a short answer. Explain why 6, 2 is on the curve. I wasn't looking for anything special here, except like the balance is the equation. It's 6, 2, isn't it? I wasn't going to be embarrassed. Yes, 6 plus 2. And 6 minus 2 cubed is 4 cubed. So this part B asks, find the slope of the tangent line. Okay, so now one of the things, this is a job for implicit differentiation, because to solve this for y is very, very complicated, right? You do this terrible thing, you get x squared plus 2xy plus y squared is x cubed minus 3x squared y plus 3xy squared minus y cubed, and you get a solve for y. And it's also really not clear, it's part of the, will be it's a cubic equation, and it's probably not going to be clear which solution of the cubic equation is considered about a lot of implicit differentiation is very, very well for us, because let's just EDX this thing. So we have 2 x plus y 1 power times what? Okay, derivative of what's inside, derivative of x is 1, derivative of y is 1. Everybody okay with that side? Okay, let's look right. 3 x minus y quantity squared. And I go through the same rigmarole. I go through the derivative inside. Everybody see the cool that? Now, here's the thing. You could go through and do all this machination. We didn't follow up this yesterday where we solved the y prime. No, I didn't ask you for what y prime is. I only care for what it is at 0.6. Right. So let's plug 6, 2 in. See what we get. Plug in 2 for, I'm sorry, plug in 6 for x. 2 y. This is 2 times 8 times 1 plus y prime equals 3. So 4, 16. 1 minus 1. So this is 16 plus 16 y prime equals 48 minus 48 y prime. And something like 64 y prime is 32 and y prime is 1/2. So solve the tangent at that point. Everybody okay with that? Now, Emery, did you want to see number C? Yeah, C is a mess, right? I will admit that's why it's a lot of problems. It's hard to get through. It's just fine. This was harder. And actually, as is always happens with these kind of things, it's not the calculus that's hard, it's the algebra. It's kind of a big it says find find the point on the curve where the tangent line is horizontal. You may ignore 0, 0. Okay, so let's write down this equation. This is where we did up my work here. Well, I realized when you all were working on the exam, there's not much time to make contemplation. But now that we've doubled the later time on it, and what happens to this equation? I plug in. What did I say to you? What happens if I plug in 0, 0 for x? What happens? I get 0 on both sides, right? I agree. The y primes disappear in all the dust. 0 equals 0 is certainly a correct mathematical equation, but it tells me nothing, right? So to analyze what happens here requires a little bit more. I have to do some stuff that you're going to do. So I'll let you sidestep that. And hopefully that'll make things a little bit easier. Okay, so I'm looking for the point on the curve where the tangent line is horizontal. I can ignore 0, 0 as a solution. So what do I do? This is the first equation I've gotten out of this problem that involves y prime. How do I proceed? What's my goal? Tangent line is horizontal. Somebody heard that. Not y. Y primes. So let's set y prime. See what happens. Check this out. So if the tangent line is horizontal, then I get so this is a good sort of technique for trying to find this out. I'm going to say, notice that if y prime is 0, then I'm going to get a point. I probably need to verify that point actually has a 0 sort of tangent there. So I'll get this equation. Right? But now what? Any ideas? Okay. I could, but this is one equation that x and y must solve or must satisfy. Right? It's more than that. Anybody think of another equation that x and y must satisfy? We've already sort of incorporated slope of the 0. So we did this auxiliary equation. Right? This thing must also satisfy the following equation. Is that wrong? Like, So how do we do this? Well, let me make a suggestion. Let's multiply both sides of this by, things might work. Multiply both sides of this equation by x minus y. And I'm going to get 2 times x squared minus y squared. Because x plus y times x minus y is x squared minus y squared. And I'm going to get here 3 times x minus y. Now, this gives me x minus y cubed is 2/3. Well, I'm going to multiply this one by 3, and 3 is x plus y squared is 3 x minus y. Let's just multiply. Now, this allows me to do some substitutions here. So now what I get is these two are equal. So I'm going to set these two equal. This equals this. Now, this is 2. So either one solution is y equals minus x, but y is not equal to minus x, then I can cancel x plus y. I get 2 x minus y plus 3. Because what I did is I canceled the x plus y here. And this condition here makes sure that that's not 0. If x plus y is 0, I can't cancel. If x plus y is not 0, then I can. Got this. And this is an easier equation to solve because this is 2x times y is 3x is 3y. And I get y 5y is minus x. So I get 2 solutions. Y equals minus x, y equals minus x. Now, I'm going to use that here to get actual numbers. I'm going to use this equation here that I got because it's the smaller of the 2. Right, this is the bigger equation. I'm going to use the smaller one. If y equals minus x, plug this in. Y equals x squared when I plug in y equals, I get 0 equal to 3 x minus y squared. And that also gives me y equals. Oh, right, and this gives me y equals x. And so if y is minus x and y equals x, this means that y equals x 0. This is not a solution. Because here we're plugging y to minus x. This equation right here gives y equals x. So if y equals minus x and y equals x, that means x is 0, means y is 0. And I said that we could pull out 2, y equals minus 1/5 x. This gives me 2 times x minus 1/5 x is 4/5 x is equal to y is minus 1/5 x. So that's 3 times 6/5 x squared. What's x minus? Right. So what does this give me? This one gives me a mess. This is 8/5 x. Is equal to 108/25 x squared. So either x equals 0 x is 0 and y is 0, and we throw through that solution. Or 8/5 is equal to 108/25 x. Means x is 5. X is 200 over 5. And this should simplify down to 24, which is 10. So x is 10/27 and y is minus 1/5 x, which is minus 2. And actually, if you check that, you'll see that you get 0 something. Right, so the algebra is difficult on this to get it. Okay, any questions? Okay, others. How do y'all feel about what the calls room? I gave you this. Yeah. Let's make this. Sorry. Okay, let's see if we can do this. I predict a big this. See if I can do that. What's the first thing to do with anyone? Right, just direct substitution, see what happens. Sine cube of 0, 0. Sine of 0, 0. So sounds like a job below the call. So I think this is. Let's do the bottom. What's the derivative of sine of log? But I'm not doing it now. So I got to multiply that. Better. All right, now we got to take care of this. Now remember, sine cubed x is sine x. I'm sorry, sine 2x quantity cubed. So the derivative of this is 3 sine 2x squared times the derivative of sine, which is cosine of x. So, okay, I'm going to write this. What do we do now? Well, we've successfully, I think, done one application for the cultural, so you can go back to the direct substitute in. If you just plug in 0, what do you get on the bottom? 0. What do you on the top? If you did get 6 over 0, that would mean this thing is fine. Done, but you don't. This piece. But 0, 0 again. Now tell me why there's big tiers of the national team full of an error at this point now. Why do you not want to do what we call it? I mean, what do you all have to do? A lot, right? Everybody agree with that? I mean, this is a product rule with chain rules. This is a product rule with chain rules. Nobody wants to be doing that. How can I make it easy? Yeah. You all told me that you got 0, 0, right? Why did you get 0 on the bottom? Because of this term. Do I agree with you? Well, in fact, let's do this. Let's say, actually, just the x squared. What I'm going to do is I'm going to kind of find something to teams. The x squared part, which is 0. What about that part? What does that give you? That would give you 15, right? So it's not really part of the process. Do I agree with that? What was it among the top that gave you 0? It's the sine squared part. The rest of it is 6 cosine 2x. That gives you a 6. That doesn't interfere with the process. So now Now, remember, we have to be a little bit careful because what we're using here is this old theorem about the limit of the product is the product of the limits. That only works if both of these limits exist. We will find out if it does. So, let me take a little aside here. I'm going to come back to this. Let's just do problematic. The limit as x goes to 0, sine 2x, actually that's sine squared of 2x over x. Let's just figure this one out separately. I may have to do it. Okay. Everybody with me? 0 of 0. I mean, that's how we picked this thing in the first place. Let's do what we call rule. 2x at the bottom. I have 2 sine 2x. Derivative of sine is cosine 2x. Notice again, 0 over 0. So I'm going to divide it up as I did before. And my offenders and non-offenders. This is under 2x 1. And I'll go sine 2x. Offender and 4 cosine 2x. 2. Now, as my last side, let's find this one. This is my last one. What is, well, again, 0 of 0. Derivative of sine 2x is what? Cosine of 2x times. I've derivative of what's inside, which is 2. Derivative of 2x on the bottom is 2. What's this limit? Is 1 over 2. So backtracking, that means this limit is 1 times 4. Right. Backtracking again, after our original mess. This thing turned out to be 4 times, what's this limit? Well, this was just a straight up plug in, 4.6 over 50. And 24/50 is now, you don't have to break it up the way I did into the offenders, the ones getting zeros, the ones not getting zeros. But I think seriously, if you start doing this, this is a 3-step what we call rule. When you do the second step, it's going to be several terms. There's going to be 2 terms out of this product rule, 2 terms out of this product rule. When we do the third step, we should probably double that, right? So there'll be 4 terms. That's not fun. Yes, you said well, if you come up, if you finally get one of these doesn't exist, And that means you probably need to rethink it. Since all these limits existed. Oh, yeah, and I'll give that to you. Well, right, so you might have been able to write this is actually sine of 4x, right? This is 2 sine theta, so this should be sine of 4x. So if you wanted to take advantage of certainly that, you could do that so as well. Yeah, actually, that's clever. No, right. If you had made that observation, that could say safety step. Here it's a little bit harder to. Okay, other questions? How about general concepts? Is there something you all feel, I don't know, like a little less comfortable with, something you're worried about? The good thing about math, though, is you usually use the previous stuff so much that you don't get completely rusty. Okay. Other questions? Oh, here's another. What about this one? Infinity. Two x. So everybody remember the fact that cosine and sine are always between 1 and -1, right? So what happens at the top of this x goes to infinity? Everybody agree goes to infinity? Right, infinity plus minus. The bottom goes to negative, right? This is a candidate for what we call here. It's 6x, 1 minus 2 sine 2x. Everybody agree with the on the bottom, I get minus 2x plus 5 plus 2 cosines. Agree? Okay, this again is x goes to infinity, 6x in here, these two small, so infinity on. As x goes to infinity, this is going huge negative, small number. So, so let's do what we call it one time. I get 6 minus 4 cosine 2x, right? Minus 2 minus 2 sine x. what do I get here? What's happening? Back and forth, back and forth. It's the rocking chair that never ends. There's all kinds of problems with this. The numerator is going back and forth between like 10 and 2, right? The denominator is going back and forth between -4 and 0. And even if this, so the denominator actually is at 0 infinitely often. Right? So this wouldn't even exist. And in fact, even if it was 0 infinitely often, the top is wiggling back between back and forth between 2 and 10, and the bottom between 4 and 0. It's not fixing on, it's not getting close to any single number, it's just oscillating. Do I agree with that? So what's our conclusion? Our conclusion is keep people right. That's one of the subtleties of multi-college rule. Multi-college rule says do this rule, do this rule. If you get a number or you get plus or minus infinity, you're good to go. We got neither one of these. Right? We just got an oscillation. What that means, unfortunately, is this is certainly a candidate for a rule, and you're not foolish for having done it. When you get to this point, it's like, it doesn't apply. Doesn't apply. So, like your eyeballs on that telling you the answer is. Who does it exist? It is -3. How did you know that? There you go. There you go. So be careful of that. Let's go through it. It's the same way that we got kind of the infinity and the minus. The dominant term here is the power 2, right? That's the Mac Daddy in the neighborhood, right? And it's totally spoken to everybody else. This is splitting back and forth between 1 and -1. This is smaller. And the big one down here is the -x². So let's multiply top and bottom, kind of have a tie here. 1/x². And this is the limit as x goes to infinity. So what do we get? 3 plus 1/x plus cosine of 2x over x². And I get -1 plus 5/x plus 1/x². Plus 2 sine x over x². Now, that's right. We know from 1040, this goes to 0, as does this and this. Why do these go to 0? Both of these limits are 0 as well. Can I explain why? Can I squeeze an answer out of it? This is the squeeze. I'll do one of these. Right. Notice that. And this is the key, and it works the same program. I'll do this. Notice the 2 sine x is between 1 and -3. No, it's not. That's better. 2 sine x over. Right. Now divide both sides by this denominator. And as x goes to infinity, both of these go to 0. So limit as x goes to 0 to sine x, or x squared, 0 plus 2. Okay, other questions? Hold fast or anything? See. See if I can pull. All right, here's a one here. All right, so I'm gonna read through this. This is problem. This is problem 3, fall 2007, exam 2. Okay, so I'll read this. The sun rises at 6 a.m. and sets at 6 p.m. It goes directly overhead. You are standing in the shadow of a mountain and notice the shadow of the mountain is decreasing at 2 feet per second at 10 a.m. How high is the mountain? What's it now? This is off my website. This is exam 2, fall 2007, problem number. What's that? Yes, that's right. So this was, I thought, kind of it's interesting that there's enough information in the problem. There's an implicit piece of information in there that sort of sun rises at 6 p.m., 6 a.m., and sets at 6 p.m. and goes directly over there. You are standing in the shadow of a mountain and notice the shadow of the mountain is decreasing at 2 feet per second at 10 a.m. So and you're standing in the shadow of a mountain and notice the shadow is decreasing at 2 feet per second at 10 a.m. How high is the mountain? Okay, so this is kind of, so you've got this 12-hour day, sun rises at 6 and sets at 6 p.m. And the sun goes directly over your head. You're standing in front, standing in the shadow of the mountain. Shadow of the mountain is decreasing at 2 feet per second. How tall is the mountain? This is actually interesting because I didn't tell you how far away. And this is And there is an assumption that we'll make here, and that is the earth is flat. Saying that, but we're just going to do this for ease. Actually, when I originally wrote this problem, I thought the last thing is instead of asking how high the mountain was, I'll say what continent. But I so let's figure this out. This is kind of a problem. So let me kind of draw something just to help me out. And don't draw anything beautiful. So here's my mountain. And I'm going to call this H for height. I don't know how tall it is, but the height of the mountain certainly doesn't change. This problem progresses, right? So this is constant. And here I am. I'm over here somewhere. And I'm in the shadow of this mountain. I'm going to call this S for shadow. Okay, so let me start kind of mining this problem with information. Sun rises at 6 a.m. So we'll say the sun rises here, it says here. So the sun goes like this. Yeah. So somebody, I need to interpret this information. Rises 6 a.m. says, how can I turn that into a piece of information that might be useful for the problem? And by the way, I don't think I'm doing late. Right. So somehow we're going to turn this. So the sun does some trick in 12 hours. As the sun does this trick, what changes? The shadow certainly changes. Or what else that I perhaps haven't played with? Certainly behind the mountain. And the shadow changes. What else? Now let me ask you this. I mean, I'm idealizing my mountain. So it doesn't look like Everest here. So cold. But that's what I'm doing. Use this to tell me something about change in data. Somebody use this information to tell me how fast is that angle? Just to visualize this better, right at sunset, my angle of theta is about 0, right? The shadow stretches almost out forever. So at noon, assuming that this is very emaciated mountain and what would theta look like? So this goes pi over 2 radians in 6 hours. So as you said, pi over 12 radians per hour. Right. Now, my S, I don't seem to know much about it, right? I don't know how far I am from the mountain, but I do know this. I do know this right here. Shadow of the mountain is decreasing at 2 feet per second. Okay, so just interpret that part. Okay. Per second, yes. Actually, very good. It's 2/3 of the way to power over 2, so you get power over 60 degrees, right? At 8, it's 30 degrees. At 10, it's 60 degrees. Well, okay, so um, I do see a problem. Yeah, so I've got hours and seconds. I guess I could do this. Minus 2 feet per second in 3,600 seconds is 1 hour. So this comes to minus 7,200 feet per hour. Okay, so now I've got everything per hour. Okay, what is my quest? I need to find out to get this info. Okay. Suggestions. What might we do? Ooh, that's a great idea. Let's try it. Right? I hate the motion rules. Let's do this. Same equation, but now the fraction take the derivative of. Well, I think I've milked this thing dry as far as getting information out of it. I know I'm looking for H. I've got this equation. Let's just take a derivative and see what falls out of this. Okay, this right here, S and theta are both changing, right? So this is product. So I get S T tangent theta plus S secant squared theta T is theta. That's what's the other side? Good. The other side is the H to T. All right. But H is the height of the mountain, which is not changing. So the other side is 0. Okay. Right. H is constant. It's just a number. So it's not changing at all. And let's see here. What am I looking for? I'm looking for the height of the mountain. There's no H in this, but there is one missing thing that I can't find. What do I know? I know theta. I know d theta dt. I know ds. So this equation, the only thing that's missing is s. I can use this equation to figure out s. Can somebody tell me why I win if I figure out what s is? You can plug it back into this formula and find out how it's all out. So let's go with this. The SDT, I improved the SDT, minus 7,200. Tangent theta is the tangent of power 3, which would be radical 3, plus s secant squared. Okay, so the cosine of power 3 is 1/2. So the secant of power 3 is 2. And so secant squared is 4, and the theta dt was whatever point. So that's the point. What's that mean? I think that's the point. You mean what secant is? So I understand why. Okay, so let me break that up. So theta is power 3, right? Secant theta is 1 over cosine theta, which is 1 over cosine power 3, which is 1 over 1/2, which is 2. Right? Now square this. So secant squared theta is 2 squared. Always take it back to the science. So now good my sign. So I get something like pi over 3s 7,000 radical 3, or s is 41,600 41,600 radical 3 that so what I get is ridiculous to do this. Yeah, I must have different numbers. Or I did it for like 11,000 feet high. 6 hours. That's right. This is 1,700. Oh, that's just yes. So H is S theta, which is S times radical 3. There we go. That's a little bit better. That's pretty well. So I get basically this time radical 3 is what I need. So this is 64,800. Let's see what that comes to. Yeah, Still didn't determine the contact. It's like a little. So, yeah, if I said you're in the United States, you would be asked. Anybody know how tall Denali is? It's like 20,000. Okay, questions? Any questions? Is that, now see, that one I think is a fairly involved like race problem. Did you all get that? So you were worried.
Finding it that bad, like broad and having my
Right. Yeah, it just requires unfortunately lots of practice. But drawing the pictures, I think, helps a lot. And make your pictures simple. It's a tool to help you out. Yeah, but a lot of the techniques, they're kind of the same over and over again. And that's what you're going to encounter in the real world, right? Crazy stuff. So. Yeah, actually, it is kind of interesting, isn't it? Because I don't know about you all, but when I first read it, so I kind of made this problem up, just kind of mucking around a little bit. And I was like, when I read the problem again, it's like, it almost doesn't seem like there's no information.
That's what most of the data grades like, and I'll solve them like, oh, never mind.
Okay, other questions? Any others?